In today's rapidly evolving world, where sustainability and energy efficiency are paramount, learning how to leverage digital twins can make a better understanding on your building's energy consumption. Digital twin model is a comprehensive virtual model that mirrors the physical entity of a building in all aspects which affect the service's performance. For example, Building Information Modeling, BIM, is a well-known type of descriptive digital twin that includes building geometry, internal spaces, and properties of building elements. Besides, Building Energy Model is a specialized type of digital twin for quantifying and evaluating building energy performance, providing a handy tool for retro-commissioning RCX. Imagine having an exact virtual replica of your building in the digital world. This twin, like a crystal ball, reflects all kinds of operational data, from thermal environment and lighting quality to indoor air quality. In a whole building energy model, a three-dimensional model is built according to the as-fitted geometry and construction of the building to accurately represent the thermal properties of the building. Annual solar path information and hourly weather data are selected based on the building site location. Architectural features and shading devices are also included to accurately estimate actual solar heat gain for seasonal cooling demand analysis. Occupancy patterns, requirements of indoor conditions, operating schedules, internal loads and gains such as lighting and electrical system are input to the model to simulate the actual operation of the building. Last but not least, all building services, installations, and other energy-consuming systems are set up in the model with the same operating patterns and control methods as in the actual building. So what are the capabilities and benefits of using a digital twin energy model? Digital twin model is capable of replicating the actual conditions of existing installations, including cooling systems, air distribution systems, automatic lighting controls, to renewable energy systems. No matter how complex your system is, it can be reconstructed in the digital twin. The model both looks the same and operates the same as it is. The model can then project and evaluate the detailed energy breakdown. For aged buildings, existing electrical system may not have sufficient submeters to provide detailed breakdown of energy consumption by services. Even power analyzers are installed, it usually has no systematic trend log as recorded. An energy model, virtual submeters could be assigned to each equipment, revealing the detailed energy consumption pattern, which then be projected for investigative usage and power consumption pattern. By importing weather data into the simulation, a comprehensive annual energy consumption projection and system performance could be obtained. The detailed energy breakdown of each system can be used specifically to analyze and diagnose system performance, facilitating the identification of specific and cost-effective energy-saving opportunities, ESOs for short. The simulated consumption profile shall have no big difference with the actual utility bill. If the utility bill record is way higher than the estimated value in simulation, it is very likely that there are equipment malfunction or control signal faults. This suggests corrective maintenance and functionality review is required to identify the root cause of increased energy consumption. In conventional energy saving calculation, simple projection estimation can only derive potential energy savings, but are unable to assess the indoor comfort conditions. This may cause a doubt or even refusal from users for the ESO implementation. Besides, it would overestimate the actual energy savings achievable, or result in discomfort and productivity loss during ESO implementation. The digital twin model simulates the thermal condition of each indoor space. Room temperature, relative humidity, carbon dioxide concentration, airflow, and other parameters can be reviewed as well in time series down to 1-minute intervals. This allows the ESOs to be refined to the most reliable implementation method to ensure that energy savings do not sacrifice occupant comfort and give confidence to users. The most powerful application of digital twin energy model is the ability to perform what-if scenario analysis. In the virtual environment, ESOs could be tested immediately at no cost prior to actual implementation, to avoid causing any disturbance to the building's normal operation. Besides, the combination effects of multiple ESOs could be simulated together to review the overall impacts and results. This helps identify the optimal point with the best energy versus comfort performance and uplifts the quality and reliability of ESO proposals. With digital twins, we can easily change the type of chiller, the air distribution zoning, downsize or upsize an equipment, or even alternate the building properties like insulation materials and window location. Simulation results give quantified performance comparison among each retrofit option and the synergic effect of combination of multiple options. Accurate energy savings estimates give better payback and cost effectiveness analysis. This allows building owners to make informed decisions before deploying the actual investments and retrofit works in the real world. But here's the catch. A digital twin is only as powerful as its accuracy. Reliability of digital twin is highly dependent on the quality and quantity of the input data. The finer and more detailed the building's operational data, the better a digital twin can match actual performance. It makes no sense to have a model with a great prediction of total consumption, but a nonsense seasonal pattern, and vice versa. ASHRAE Guideline 14 sets the international acceptance level for whole building energy model calibration. Remember, the digital twin acts as an insightful crystal ball that reveals how your building is operating. Uncertainties and errors will turn the crystal ball cloudy, thus losing the ability to explore ESOs. Collecting quality and sufficient data is always the biggest challenge in developing a reliable digital twin. Once you have the right set of data, digital twin energy models will be a handy tool to create smarter, efficient environments